values here, alpha 1 into mu v1 minus mu r1 is equal plus alpha 2 into mu v2 minus mu r2 is equal to 0, implying alpha 2 is equal to minus alpha 1 mu v1 minus mu r1 divided by mu v2 minus mu r2. So, alpha 2 is equal to minus alpha 1 into mu v1 minus mu r1 by mu v2 minus mu r2 is this. Here mu v1 definitely greater than mu r1 because refractive index of a given material for violet is more than red, thereby violet is bending more. So, therefore, this quantity is a positive quantity, this quantity is also positive quantity, therefore, quantity in the bracket is positive. But angle is coming out to be negative. What is that negative angle? The second prism must be attached to the first prism inverted. The arrangement should be like that. If we have a first prism like this, prism angle alpha 1, then second prism we should connect it like this, attached to the first prism such that it is inverted. Means the angle to be measured here is anti-clockwise, this anti-clockwise angle measurement is opposite. So, therefore, the prism angle alpha 2 minus sign indicates second prism has to be inverted. This is prism 1, prism 2. That is the arrangement. When we choose angles of the prism in accordance with the refractive indices of the materials like this, the combination now behaves combination with no dispersion, means achromatic combination now. When achromatic combination, when we choose the angle like this, no doubt we get no dispersion, but resulting deviation will be there. So, what is going to be the resultant deviation of such a combination? Therefore, the resultant mean deviation produced by such a combination is resultant mean deviation is equal to mean deviation produced by the first prism and mean deviation produced by the second prism, sum of these. Both prisms are used, therefore, mean deviation produced by the first prism and mean deviation produced by the second prism is the resultant mean deviation, delta mean deviation. Substituting here what we get, alpha 1 into mu v1 plus mu r1 by 2 minus 1 plus alpha 2 into mu v2 minus plus mu r2 by 2 minus 1. So, this is the mean deviation produced. But alpha 2 just now we have calculated, but alpha 2 is equal to minus of alpha 1 into mu v1 minus mu r1 by mu v2 minus mu r2. So, substituting this alpha 2 value in this equation, whatever the deviation we get, that is the mean deviation of such a combination of prisms where deviation is there but with no dispersion. Without dispersion, we are able to get this much of deviation. That is the first combination. Now we go for the second combination. What is the second combination? Second combination is direct vision, that is dispersion without deviation. Second case we can say is dispersion without deviation. Dispersion without deviation. In this case, we don't want the total deviation, we don't want total resulting deviation. Means deviation produced by the first prism, mean deviation produced by the first prism, and also mean deviation produced by the second prism. Both the prisms are producing, but together total deviation produced by the combination should be 0. It should be 0, that is the requirement for no deviation. For no deviation, the deviation produced by the first prism, deviation produced by the second prism should be 0. Substituting here alpha 1 into mu v1 plus mu r1 by 2 minus 1 plus alpha 2 into mu v2 plus mu r2 by 2 minus 1. Therefore, from here alpha 2 is equal to minus alpha 1 and mu v1 plus mu r1 minus 2 divided by mu v2 plus mu r2 minus 2. Here also we get alpha 2 coming out to be negative when compared to alpha 1. Means in this case also first, in this purpose also, the second prism should be attached to the first prism inverted. But for this purpose, prism angles should be related by this equation. Earlier relation is different from this. Now the prism angles should be related by this equation. When we choose the prism angles in accordance with the refractive indices by this equation, now the combination will have no deviation produced. Resulting deviation produced is 0. Now what happens to that combination? Now behaves a combination with resulting dispersion. So now we calculate what is the resulting dispersion of such a combination. So therefore, the resultant angular dispersion of the combination. Resultant angular dispersion is equal to angular dispersion produced by the first prism and angular dispersion produced by the second prism of combination where this condition is satisfied. So now we will calculate it. Angular dispersion produced, here it is alpha 1 into mu v1 minus mu r1 plus alpha 2 into mu v2 minus mu r2. But alpha 2 just now we have calculated as minus alpha 1 into mu v1 minus mu v1 plus mu r1 minus 2 by mu v2 plus mu r2 minus 2. Substitute this alpha 2 here. This is mean or resulting angular dispersion produced by the combination. By properly choosing prism combinations, means by choosing proper angles of refraction angles and proper materials depending upon the materials, by choosing proper angles of the prisms, we can have combination of prisms producing the required result. That what result? Either resulting dispersion or resulting mean deviation. Means one of the effects we can have, though prism can produce both the effects simultaneously. Okay, this completes refraction of light at plane boundary completely.
Dear students, ఇది ఇవాల్టి ఫిజిక్స్ క్లాస్. ఈనాటి ఎపిసోడ్లో జామెట్రికల్ ఆప్టిక్స్కు సంబంధించి కొన్ని అంశాలను తెలుసుకున్నాం కదా. మరి రేపటి ఎపిసోడ్లో మరొక ఇంట్రెస్టింగ్ టాపిక్తో మీ ముందుంటాం. టిల్ దెన్ కీప్ వాచింగ్ KAB టెలివిజన్.